Okay, so there are a few so-called laws of set algebra or set operators, and are really nothing more than logical consequences of what we've defined, but they're useful to know because they're things we can depend on. So let's take a look at a few of these. A couple of them we've already mentioned. One is the fact that these two operators, union and intersection, are commutative. And again, commutative just means that if you reverse the order of the operands, you get the same answer. So it's guaranteed that A union B is going to be the same as B union A, no matter what A and B are. Turns out these are also associative, which is a different property. Associative basically means that if you have a string of them, like A union B, union C, union D, it doesn't matter which one you do first. So you could say, well, let's do A union B, and then let's union that with C, and then let's union that with D. And if I do that, I'm going to get the same answer as I would if I said, you know, let's postpone the whole A union B thing because I'm not in the mood to do that. But I really want to do B union C first. And then once I've done that, then we'll union that with D. And then finally, we can deal with that whole dastardly set A. You're guaranteed to get the same answer that way too, because union is an associative operator. And intersection is also associative, just like that. All right, there's also a property. You've probably heard of a lot of these in grade school, depending on what teacher you had. You've probably heard of the distributive property. And in algebra, it looks like this. A times B plus C is the same as AB plus AC. And that's not because math teachers made that up. That's because it just works out that that's always going to be the same answer. And so you can guarantee that this identity is true. Turns out the same thing is true for intersection and union. So if I say X is a set, intersect that with the set Y union Z. So if I take Y and Z and union those two puppies so that I get a set that has all the elements that are in either one, then I intersect that with X, I am guaranteed to get the same answer as X intersect Y, union that with X intersect Z. And if you squint a little bit, you will see that these two have exactly the same form. That I've got plus two things, then times it by this guy. That's what's going on here. We're unioning two things and then intersecting it by somebody. Then on this other side, I'm saying, well, let's times two things and let's times another two things and then let's add them together. That's what's going on here. I'm intersecting two things, intersecting another two things, and adding them together. And in fact, there is this really deep relationship between intersection and times, you know, we sometimes write that as a dot, and between union and plus. In fact, this runs really deeply, and it actually goes into logic as well. And we're going to see that the role that the intersection operator plays is really the same role that times multiplication plays, and that the role that union plays is really the same as the role that addition plays. And here's one of the many, many places where that kind of comes up, because here, if I replace A, B, and C with sets, and I replace plus with union and times with intersection, I actually get this distributive law like that. So it's one of the many fascinating places in math that this sort of distributive property holds between two different operators. Interestingly, there is another distributive law that also holds, that is not true in algebra, but is true with these sets, and that is the same thing if I replace the intersections with unions and vice versa. So it turns out that X union intersection, or Y intersect Z, is the same as X union Y intersect Y union Z. And that is not true in math, right? It's not true that I can say A plus B times C equals A plus B times A plus C. That's nonsense, right? That doesn't work. But in fact, it does work in set algebra with this formula here. So if we want to see this as an example, just for some extensional examples, what if we said X is 1, 2, 3, and we'll say Y is the set 3, 4, 5, and we'll say that Z is the set 3, 5, 1. All right, let's just test this out to make sure it works. So we're trying to verify that indeed X intersect Y union Z. does in fact always turn out to be a set with the same members, the same extension as x intersect y union x intersect z. So let's just kind of verify this here, right? So if we figure this out first, y union z, that is going to be the set that has all the elements that are either in y or z or both, which is going to be 1, 3, 4, 5. Right? All I did was take these two sets and union them together. If I then intersect it with this guy, I'm going to get only the elements that are both in x and in 1, 3, 4, 5. And if you work that out, you'll realize that those are the elements 1 and 3. Those are the only elements that are in both x and in y union z. Okay, so that's what we get on the left-hand side of the equation, is that thing. Now, let's work out the right-hand side of the equation here. If we take x intersect y, we're going to get only the elements that are in both x and y, which looks like it's 3 is the only one that's in both those sets. If we take x intersect z, we're going to get only the elements that are in both x and z, and it looks like 1 and 3 are the two elements that are both in there. And then if I take the union of those two, I'm going to get the set that has any of them, or any elements that are in either the left or the right or both, which is 1, 3, and that is, of course, exactly what we got over here. And you could similarly work it out for that other equation where you replace the intersects and the unions there, and it turns out to be the same. If you want another example that's more of an intentional example to kind of get some intuition like this, we might say, let's let x be the set of female UMW students, so the set of females, and we could say let y be the set of computer science majors, and we could say let the set z be the set of math majors. So suppose those are our three sets. We're specifying them intentionally now, not extensionally, because we want to make sure that this aligns with our intuition. Does it in fact make sense that x intersect y union z would in fact be equal to x intersect y union x intersect z? So here's the way you think about this. You say, well, what is y union z? Well, that's all the people that are majoring in math or computer science, or both. So double majors in math and computer science are certainly in this set. Also, people who are just majoring in computer science are in this set. Also, people just majoring in math are in this set, right? So these are all of the geeks, maybe you'd say, right? And by the way, I take pride in the word geek, so I don't mean that as a pejorative in the least. So Y union Z gives us all the people who are majoring in either math or computer science. Okay, and then X is the set of females. So if I take the set of females and I intersect it with the people who are majoring in math or computer science, then essentially what I'm getting here is the female geeks. Okay, so does that align with our intuition about the other side? If we take X intersect Y, then that's giving us the female computer science majors. And if I say X intersect Z, that's giving us the female math majors. So if I take those two sets and union them, then what I'm going to get together is I'm going to get the females who are majoring in either math or computer science, which again are the geeks, if we use that term, right? So either way, it comes out to be the same thing. It just depends on which sort of thing you do first and how you combine them, but you can sort of see that intuitively they wind up being the same thing. All right, so that's the distributive law, and again, you can work that out with the other example where we switch intersection and union. All right, now a couple easy ones here. There are the identity laws, so-called. And that simply tells us that X union empty set equals, figure that out for yourself, X. Because all we've done is taken a set X, we've unioned it with nothing, so we've said also add to this set anything that's in the empty set, if it doesn't already have it, but of course there isn't anything in the empty set, so we're going to end up getting X. So that's an identity law, meaning that unioning with the empty set basically accomplishes nothing. And similarly, intersecting with the domain of discourse accomplishes nothing. Because everything is in the domain of discourse. So if I say, let's take some set X and intersect it with everything, that just means give me the elements that are both in X and also in everything. Well, everything's in everything. So basically that just boils down to X, which are the elements that are already in X. So that's another one that's sort of a logical conclusion to this. Now we have the complement laws. And this says that X union X bar, so remember, X complement means the set of things that are not in X, so everything except X. This tells us that if we take X and union it with the complement of X, we get, work it out for yourself, the domain of discourse. Because this is saying, let's take everything in X and everything not in X, put them together, what do we get? Well, we get everything. If you take the set of blind platypi and intersect it with the set of everything except blind platypi, you get the set of everything. If you take the set of, wizards with 5 fingers on their right hand and 6 fingers on the left hand and intersect it, or union it with everything except wizards with 5 fingers on the left hand and 6 fingers on the right hand, you get everything. Okay, so this is guaranteed to work for everything. And then similarly, if I take X and I intersect it with its complement, I'm going to get the empty set. Because that says if I take the set of, all peanut butter and jelly sandwiches and intersect it with the set of everything except peanut butter and jelly sandwiches, then I'm of course going to get nothing, because nothing is in X and in not X. That's the definition of the complement of X, is the things that are not in X. All right, there are also the so-called domination laws. Ooh, baby, we're going to dominate. The domination laws say the following. If I take X and I union it with the domain of discourse, I'm going to get the domain of discourse. So the domain of discourse dominates here, right? If I say I'm going to take anything that's either in X or is in everything or both, then of course I'm just going to get everything. X doesn't even matter at that point. So that's kind of the reverse of what we had before. And similarly, if I intersect something with the empty set, well, then the empty set dominates. Because now I'm saying, well, I only want the things that are both in that set X, the set of all prime numbers that have 4 digits, and that are in the set of nothing. Well, nothing satisfies that, and so you end up getting the empty set back. Finally, there are De Morgan's laws. And these are not quite as obvious to see as first glance as some of those other ones. Here's the first one. X union Y complement that equals the complement of X intersect the complement of Y. Okay, now why would that be? Let's work it out with an example. Let's say X is the set 1, 2, 3. And let's say Y is the set 3, 4, 5. Okay, so we go over here and just kind of crunch the numbers. What do we get when we get this? Well, X union Y is going to be 1, 2, 3, 4, 5, because that's all the things that are in either X or Y, or both. Now, what's X union Y bar? Well, of course, that depends on what the domain of discourse is. If the domain of discourse is absolutely everything, then what we get here is the set of absolutely everything except the integers 1 through 5. If, on the other hand, our domain of discourse is the numbers, then we're going to get all numbers except 1 through 5. So let's kind of make something up here. Let's just say our domain of discourse right now is the numbers 1 through 10. Say that that's what we're considering. That's our domain of discourse. Okay, well then X union Y bar is going to be 6, 7, 8, 9, 10. Right? Those are all the numbers in our domain of discourse that are not in X union Y. So that's what we get on the left-hand side of this equal sign. Now, what do we get on the right-hand side of the equal sign? Well, X bar is going to be the set 4 through 10. Right? Because X is 1, 2, and 3. Therefore, X bar, or X complement, is going to be all the numbers in our domain of discourse except 1, 2, and 3, which are 4 through 10. What is Y bar? Well, Y bar is going to be 1, 2, 6, 7, 8, 9, 10. Because Y has 3, 4, and 5 in it, therefore Y bar is going to be everything except 3, 4, and 5. And so we get that. And then at last, we're going to intersect x bar with y bar. So that's going to tell us to give us everything that is in both this set and this set. Well, if you think that through and ask what numbers are in both of those, they are going to be the numbers 6, 7, 8, 9, and 10. Those are all of the elements that are in both sets, and only the elements are in both sets. And of course, this is equal to that, which proves the first of De Morgan's law. And the second one is like it. It says that x intersect y bar equals x bar union y bar. So it's the same law, except we've just switched the intersections and the unions. We've interchanged them with each other, and that also turns out to be true, and you can work that out. And there's also an intuitive explanation for that. If you look at it, you can think in terms of, what if X is the set of females and Y is the set of computer science majors, and you can kind of work through in your mind, why the left side would equal the right side, why this would end up being the same. So let's do a little bit of quick review now. Okay, so we have these three sets here, U, M, and W. What do we get if we intersect U and M? Stop the video and figure it out. Answer is we get the soccer ball and the stop sign, since those are the only two elements that U and M have in common. What do we get if we do U union M? That gives us everything in both sets, including the numbers and all of the figures. What about M intersect W? Obviously, you can't figure that out extensionally because you can't enumerate all of the things in the set W. It's infinite. But you can figure out that the only thing that M has in it that is in common with the even integers is the number 4. What happens if we intersect all three of them? We get the empty set because there isn't anything that all three have in common. What if we have U minus M? That's going to give us all the elements of U except the ones that are in M. The 4 and 5 don't really enter into it, but the stop sign and the soccer ball get subtracted off. What about M minus W and then minus U? Figure that one out. That's going to give us 5. Because if we take M and we subtract off W, that we've gotten rid of the 4, because that's the only thing in W that was also common with M. So now we have stop sign, soccer ball, and 5. We subtract off U, gets rid of the 2 figures, and now all we have left is the number 5. Let's add a couple more sets here, V and A. What do we do if we get V cross A? Remember, that's kind of a tricky one. We get ordered pairs back, not elements. So what we have here is the ordered pair George Washington, the ordered pair George Lee, the ordered pair Robert Washington, and the ordered pair Robert Lee, because those are all the combinations of an element from V and an element from A in that order. What do we do if we get U intersect M and then cross that with V? Now we also get 4 ordered pairs, which is the soccer ball and the stop sign cross-producted with George and Robert. So we get the Cartesian product, which is those 4 ordered pairs of each combination of each. Make sure you look through that list and understand how we got all those. Now what about this? Take a moment to figure this one out. Hopefully you didn't actually do all that. Hopefully what you did was said, oh my goodness, what's all this monstrosity here? And then looked at the end and said, oh, you know what? We're intersecting with the empty set at the end, so I don't even need to figure out all that stuff. I know that the answer is going to be the empty set. That's kind of like having a whole bunch of numbers you have to multiply together, and then the last one you multiply by 0. That tells you it's not even worth doing all the first ones. It's really a trick your teacher played on you. And, all you have to do is say, oh, well, the answer is going to end up being 0. It doesn't matter what everything else is, because if I multiply anything by 0, I get 0. Here, if we take the intersection with any set and the empty set, we are going to get the empty set, because the empty set has no members. Therefore, nothing is common to it and any other set. All right, switch gears here a little bit. Let's say we've got omega is the set of letters in the alphabet. So we are going to figure out that we're talking about letters here. And V is the set of vowels. What is the cardinality of V? That is obviously 5. There's 5 vowels, although my English teacher, Mrs. Rieger, taught me that sometimes Y, but I'm leaving this out of this example because that always confused me. What is the cardinality of the complement of V? That is going to be 21. because there are 26 letters in the alphabet, as I'm sure you know. 5 of them are vowels. That leaves 21 left for consonants. Exercise for the reader. Can you name all the consonants? And therefore, the cardinality of the complement of V is 21. And last one, what is the cardinality of V cross V? And the answer is 25. There are 25 ordered pairs. One of them is A, comma A. One of them is A, comma E. One of them is A, comma I. Somewhere in there is O, comma O. Somewhere in there is U, comma E, etc. There's every combination of a vowel in the first place and a vowel in the second place, leaving 25 total ordered pairs.